Hi guys, Buckley here. We're going to do some proofs here of the dot product and the cross product. And I didn't go into this during lecture because I don't like to take up class time with proofs because I feel like there's more important things we could be doing. And you may have seen this before in a math class. If you have, feel free to skip the video. But if you haven't, you might pick up a thing or two about how the dot product and the cross product worked. It's just an interesting way to see where these constructs came from. Okay, so we're going to start with the dot product. So we'll call this proof of dot product. Okay, so we start with the definition of the dot product. Okay, and that's sort of like, I've been joking in class, coming down from on high, right? The Greeks from on high. Whoever invented this, I don't think it was the Greeks, but A dot B by definition is equal to the magnitude of A, the magnitude of B, cosine of the angle in between those vectors. So we're talking about, two vectors. Say that's A and that's B. They exist in 3D space. That's the angle in between them, okay? And that's our definition, right? What we want to get to, right, is with this proof is basically the equivalent between this statement here and this last part, which is AX, BX, AY, BY, AZ, BZ. Okay, so connecting all three elements of this, right? The vector representation, the definition, and then the component form is super, super important. That's what we're going to do in the proof. Okay, so in addition to this statement here, which is the definition, we have three properties of the dot product that hold. I'm not going to go into the proof of the properties because that's just boring. But basically, you've got your commutative property, A dot B is equal to B dot A. You've got a scalar multiplication. Let's say we have a small scalar value. I'm going to call it alpha just for clarity. A dot B. That's going to be equal to alpha A, that quantity dotted with B, which is equal to A dotted with alpha B. So that scalar value can be distributed throughout. And then the last is a vector distributive property, which says that A dotted with B plus D. So we'll call D is another vector. So if I'm bringing a third vector into this mix here, I would get A dotted with B plus A dotted with D, right? A dot B, that quantity plus A dot D. Okay, and you've probably seen a lot of these from math classes, right? It's just kind of setting up the properties that go with that definition. Okay, so this stuff I'm going to box because it's sort of like set in stone for the rest of the proof. Okay, and again, our goal is to get to this. How did we arrive at the fact that A dot B with this definition gives us the sum of the multiplication of the two components? How did we do that? Okay, so we are going to first look at how, well, actually, we'll start by writing out the vectors in component form. So A is equal to AXI plus AYJ plus AZK. And B is equal to BXI plus BYJ plus BZK. So the dot product between them, A dotted with B, is really this big old mess. AXI plus AYJ plus AZK. Dotted with BXI plus BYJ plus BZK. Now we're going to make use of two of these properties, right? So we're going to make use of this guy here and this guy here to start distributing this out. And I'll write it for like the first line, okay, and then I'll just write etc. because you kind of get the idea. Okay, so I'm going to start by saying this first component, I'm going to take this guy, AXI, and dotted with every element in this expression, right? So I'm going to have AXI hat dotted with BXI hat plus BYJ hat plus BZK hat plus, now this term, AYJ hat dotted with this same expression, right? Dot, 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 plus AZK hat dotted with dot, 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 dot. Okay. So you can see kind of where I'm going. Now I'm going to distribute this across each of these other elements, right? So this is going to be this guy dotted with this, plus this guy dotted with this, plus this guy dotted with this term, right? This is a good time to pause and to look at how the unit vectors behave, right? So this term, we've got two scalars, and then really the meat of it here is the statement I dotted with I dotted with J, and I dotted with K. Well, right away, we know that these guys are also true, right? So we can flip them around. So it doesn't matter which order it's in. That's a property of the dot product. That's this guy up here. But what does I dot I equal? What's I dot J? Okay, so for that, we're going to go back to the definition of the dot product. So I dotted with itself is equal to the magnitude of the first vector, which is going to be 1, the magnitude of the second vector, which is also going to be 1, cosine of the angle between them. Now, in this case, right, so remember, these are real things, right? So if this is X and this is Y and this is Z, I is this direction here, J is this direction here, and K is that direction there. So I dot I, it's the same vector. This angle is going to be 0, right? What's the angle between a vector that is itself, right? The angle between that is 0. So cosine 0 is 1. So I get I dot I is equal to 1, right? This is going to be the same for J dot J and for K dot K. All of these are equal to 1. So anytime you're dotting with itself, it's equal to 1. Anytime you're dotting with a vector that is any of the others, any of these unit vectors, right? So I dot J, we have magnitude of I is 1, magnitude of J is 1. Cosine of the angle between them, the angle between them is 90 degrees, right? I and J, this angle is 90 degrees. Cosine 90 degrees. Cosine of 90 is equal to 0, right? It's equal to 0. So anytime you have a different vector dotted with itself, a different unit vector, standard unit vector dotted with itself, it's going to be equal to 0. So this is 0, this is 0, right? JK is 0, J dotted with K equals K dotted with J is equal to 0. So you can kind of see where we're going here, right? If we apply what we know here, every time you've got a component dotted with itself, AX I hat dotted with BX I hat dot I hat is going to be 1, right? And that'll leave AX BX plus AX I hat plus BYJ hat, I hat dot J hat is going to be 0. So any terms that are mixed, right? I hat with J hat, I hat with K hat, J hat with I hat, J hat with K hat, those are all going to fall out. So at the end of this, what you're left with, if I work with this whole form and I apply these concepts here, is AX BX plus AY BY plus AZ BZ. So only the terms that represent the component along that vector dotted with the same component along the other vector. Okay? So that's the very sketchy, okay, this is obviously I didn't do every single step, but you get the sense of how we went from the definition of the dot product plus some of its laws, right, some of its properties, to the component form. Cool? All right, so with that in mind, I want to do the same thing, but for the cross product. So let's move on to I'm going to put proof in quotes here, just in case a math professor sees this, because it's a very sketchy proof, right? But the proof of the cross product. Okay, so for the cross product, again, we're going to physically be dealing with two vectors in space, A B. There's an angle between them. This is 3D space. What we're doing here is A cross B, by definition again, by definition, is equal to magnitude of A, magnitude of B, sine of the angle between them, U hat C. U hat C, so is A cross B. Any two vectors exist in a plane, right? They exist in this plane. I'm going to pretend for a sec that A and B are drawn in the plane of this board, but there's a third dimension, right? So A cross with B would give me a vector C, which is its cross product, right? C is equal to A cross B, which is this. U hat C is the unit vector along C. It's the unit vector associated with C. In this case, this would be, C would be pointed out of the plane of the paper that I'm working on here. Okay, so just like we did with the dot product, there are some properties of the cross product that we have to be aware of. A cross B is equal to the negative of B cross A. And we can kind of see that by the right-hand rule. A cross B is going to point out of the board. B cross A is going to go into the board. Okay, so the order here matters. It's not like the dot product where I had A dot B is B dot A. The order matters, okay? Scalar multiplication works the same way as the dot product. Alpha A cross B is equal to alpha A cross B is equal to A cross alpha B. So I can distribute that scalar anywhere in the mix I want to. Distributive also works similarly, right? So if I have A cross B plus D, bringing a third vector into the mix here, I'm going to get A cross B plus the vector sum with A cross D. Okay, so these are kind of my things that I need here, right? The definition and the properties associated with it. All right, so I'm going to do the same thing I did for the dot product, and I'm basically going to express A cross B with A and B in their full component form. So I'm going to get AXI plus AYJ plus AZK cross BXI plus BYJ plus BZK. All right, now I'm going to make use of this guy again and this guy to show how it's distributing. I'll write the first couple. Okay, we're going to basically expand this out, distribute this out. So this would be AXI hat crossed BXI hat plus BYJ hat plus BZK hat plus AYJ hat cross, same term, BXI hat, same guy, plus AZK hat cross this same term as above. Okay? All right. Now we do the same pause. We want to look at how the unit vectors behave with the cross products. Because what's going to happen here is this is a scalar, so I wind up getting I cross J, I cross K, J cross I, J cross J, J cross K, right? So what are those? Okay, so I'm going to draw my axes here. This is X, Y, Z. So this guy here is I, J, K. So let's start with I hat cross I hat. That's going to be equal to 1, 1. So magnitude, magnitude. Sine of the angle between them. The angle between them is 0, right? Sine of 0 is 0. Okay, so I don't care what else is happening. This is all 0, okay? But then the U hat, right? But this term is 0. Big goose egg. I cross J gives me 1, 1, sine. In this case, I and J, they're 90 degrees apart, sine of 90. Sine of 90 is 1. Now don't forget that there's a vector associated with it. The vector is, so if I go ij, I get k, right? Let me show I, j, I cross j gives me k, right? This direction. So I'm going to wind up getting k hat here. By this property, I know that j hat cross I hat is equal to negative k hat, right? If I use this guy. So I've killed two birds with one stone there by using that property. All right, if we keep going, okay, you'll wind up with things like k hat cross I hat. K cross I is going to give me j. K cross I gives me j, right? And it's reverse, I cross k equals negative j. Okay, so there's a whole bunch of combinations of these. So what happens by the end is you get the following. So if I apply these concepts up here on my expanded form, I wind up getting A cross B is equal to AY BZ minus AZ BY I hat minus AX BZ minus AZ BX J hat plus AX BY minus AY BX K hat. That's the full expanded component form of the cross product. Now, you have a decision here, folks. You can either remember this, right? Remember that this is the form, or what I do is I say, okay, I don't remember this, right? I don't remember, it's AXBY minus AYBXK. I could put some effort, I'm sure I could, but I've always done it where it's just the determinant, because conveniently, let's do our determinant shorthand. A cross B, if I set up my determinant, IJK, my little determinant trick, right? I get AX, AY, AZ, BX, BY, BZ. So for I, I'm blocking this column and this column. I get AY, BZ minus BY, AZ. AY, BZ minus BY, AZ, I hat, right? These two terms are the same. Look at that. Okay, minus, now for J, right? Boom, boom, those knock out. Minus AXBZ minus AZBX. J hat plus, right? So those terms match up. For K, AXBY minus BXAY. XBY minus AYBX. J hat. Okay, so this is nothing more than a trick, folks, right? This is a trick to not have to remember it in this form. If you can remember the pattern for taking the determinant, you don't have to remember it in the long form. Okay. All right, guys, that was what I had for you for the quote-unquote proofs of the dot product and the cross product. There you know. The more you know.